All right, well, let's get started. Welcome everybody to today's webinar. My name is Alex Razumov, and today I'm going to be talking about running parallel array workflows on HPC clusters. I put the link to the notes on the that is on my screen into the chat, so you can actually open that page, and that page is gonna stay there, so you don't have to take notes frantically. So everything is going to stay online. Ray is a framework for scaling primarily machine learning applications written in Python across multiple computing cores. And even though the main usage of Ray is machine learning, I find that it's really great for non-machine learning workflows. And today, that's what I'm going to be talking about, how to scale general computing workflows, not outside of machine learning, using Ray, both on a single node and across multiple nodes. So I'll be talking about two different problems. One is a loosely coupled parallel problem. So that is a problem where there is not a lot of communication between different workers. So basically, you split the problem, and then each worker computes its own part, and then you collect the result. And also, in the second half of the presentation, I'm going to be showing a tightly coupled parallel problem. So we'll be solving a heat diffusion problem in 1D. And so this is the problem where you're running iterations, and then at each iteration, you're exchanging data between neighboring processes. And this, of course, takes a lot of a lot of bandwidth, well, a lot of communication. And it turns out that Ray is actually excellent about parallelizing this problem as well. So you can do it entirely in Ray. But let's get started. So how do you install Ray? On a production HPC cluster like Cedar, Graham, Beluga, and other clusters in the Lion system, you don't really have to do anything. It's already installed as one of the Python wheels. So essentially, this is what you would do if you were doing this from scratch. So you will need to load the latest modules. So there's a Python module, Arrow. So Arrow is this nice software from Apache that Ray uses underneath. And then I think one of my examples in the past actually included NetCDF. And sure, I should probably remove NetCDF because I don't think I'm going to use it today. And CyberStack, this is primarily for loading NumPy, right? So essentially, you load all the necessary modules, and then you create a virtual Python environment. Then you source that environment, so you will run these commands on a HPC cluster. And then optionally, you can upgrade PEEP, the Python package manager, and then so today I'm going to be showing examples. The first example is going to be using Number just-in-time compiler. So that's why I'm installing Number here. And in general, if you want to install any packages that we have already, Python wheels that we have already compiled for our clusters, you can run the command avail wheels to check whether it's available on our cluster and which versions we have. And so, for example, if you're curious about Ray, do we have Ray? The answer is yes. You can run this command, and then you can install it using this pip install command, right? And then in the future, to use this environment, after you exit from it, so you just log into the cluster, let's say, first you need to load the modules, and then you will source the environment, and then you start Python and import Ray and start doing the computing. So today, I'm going to show you a lot of examples on a cluster, but first I'm going to show you examples on, while I'm debugging the code, I'll show you some examples on my notebook. And installing Ray on a notebook is easy as well. So there, I mean, it depends on your preferred Python installation method. So recently I switched to a command line utility called pyenv, and it exists for all operating systems, for Windows, Mac, Linux. I'm on a MacBook, so I just open a terminal and then run these commands inside the terminal. But essentially, pyenv lets you switch easily between different versions of Python, really handy. And then once you pick up a version of Python, you create a virtual environment. And then again, I install Ray and Number. So the two packages that I'm going to be using today. So let me jump. So first, I'm going to start the demo on my laptop, and then I'm going to do a little bit debugging, and then I will show you how to run these codes on one node and across multiple nodes on a HPC cluster. So to initialize Ray, all you need to do is, so here I already loaded my environment and running this on my own computer. So I'm going to start Python, and then to initialize Ray, I simply say import Ray. And then you would typically start a Ray cluster. So I'll explain, you will understand throughout this webinar what a Ray cluster is. But in this case, we're just starting a Ray cluster trying to utilize multiple CPU cores on this computer. So strictly speaking, this command is no longer necessary because once you start using Ray, it will start array cluster underneath. But until recently, actually, I had to run this ray init command explicitly. And what it does, it starts a bunch of, so it starts a so-called ray cluster with a bunch of workers. How many workers? Depends. So when it runs this ray init command, it probes the environment on your machine. And on my machine, I have 8 CPU cores. So in fact, if I switch to a different shell, if I run htop filter, and I'll be showing CPU usage in all processes called re-idle. So these are this is what the workers are currently called. They're not running any workloads yet. So they're all called re-idle as far as the operating system is concerned. So if I show this, you see that there are 8 workers, right? So there are 8 listings here. And by default, it just found, when I ran ray init, it just found the 8 CPU cores, so it decided to start 8 workers. Of course, on an HPC cluster, it will be different because typically you run jobs inside a job, a slum job, so you don't have access to all physical cores on the system. I'm going to show you how you can work around that. So let me restart Python. And this time what I'm going to do is I'm going to import ray, but then I will pass a couple of flags. So I find that ray itself is very verbose, so it outputs a lot of information, and a lot of this I just don't need. So I like passing initializing ray with the following flag to turn off all this verbose logging. And then I'm going to initialize 2 processes. I'm going to say that I'm going to use ray on 2 CPU cores. And then once it initializes it, now if I switch to a different shell and do top on ray idle, see there are only 2 ray idle workers sitting there. And that makes sense. All right. So in ray, there are different ways to do remote calculations. One of the main ones is is to use ray remote functions. So remote function is essentially a Python function that you run somewhere else. Well, not on the current processor, but on one of the workers that are utilizing one of the other processes or one of the other nodes on HPC cluster. So how do you do that? Well, let me reinitialize, restart ray once again, so I can use multiple workers. And then I'm going to import ray, and then I'm going to initialize the cluster. And then here I'm defining the function, and this function has a decorator add ray remote. So what this decorator does, it modifies the function, and essentially it makes it a parallel ray function. And then when you run it, you will get a ray task, which is running on one of the workers. So this function takes x and returns the square of that number. So very easy, right? And then to run it, you cannot simply run it like this. That won't work. It will say you remote functions cannot be called directly. Please use this notation, square remote. Well, that's fine. So we can see square dot remote 10. And then what it does, it launches the function, but it doesn't return the result. So to get the result, you actually have to pass the output of, so the handle, which is called the object reference of this task, to a variable. And then if I inquire about the type of variable, you'll see that it's an object reference. So it's a future type variable that also doesn't contain the result, right? So if you print it, well, there's no result there. So in order to get the result, you're going to say ray get of r, and then it will get the result. So we pass 10 to the function, right here, and then the function returns the square of that number. So you do that by ray get call. So when you call the get function, it is a blocking function in the sense that it will not return until you have the result, and the result can be printed on the screen, right? So in practice, what happens often is when you call the function in a remote function execution in ray, this call actually doesn't start computation. This call doesn't start computation, but computation starts once you start using the result, right? So in this case, we're forcing the printout of the result, and then that's where typically the computation will start. So in that sense, ray remote function have lazy execution model, right? They get executed when you actually need the result. So once you initialize a remote function, you can cancel it, right? So here's a simple code where I try to calculate the square of 10 via array remote function, and then I cancel it, and then I try to get the result, right? So the end result of this cell is it actually returns either 100, so the square of 10, or it will return an error saying that the function was canceled. And which one it will return, I actually don't know. Look in the code, it depends on the runtime situation. So if it manages to cancel the array remote function before I get the result, then I'll get an error. Otherwise, I'll get the result, right? So let's see. Well, I get the result. So it actually ran before I ran cancel. So now, if you want, we have access to multiple Ray. Right now, I started Ray init, not specifying the number, of course. So we have access to 8 remote workers, right? So that means that we can actually do calculations on 8 workers. So let's do something like this. Let's do this via an array comprehension. So here we have actually list comprehension. Sorry, that's Python. So here we have a Python list where we're simply cycling through all numbers from 1 to 4. And we're starting 4 instances of the remote function running on 8 available CPU cores, right? And then the result, so you can actually, this is an array, right? That's an array. And then you can actually pass the output of that to R, and R is going to be an array as well, right? So it's an array of future references. So here we started 4 remote functions. And then if I print R, of course, it doesn't contain the result. Again, these are references. So in order to get the result, what we can do is we can say array get of, let's say, R of 0. So the index in Python goes from 0 to 3 in this case. And so here we get the result 0 squared. Let's say 3 squared is going to be 9, and so on. So of course, these are blocking calls, right? These are blocking calls. If you want to get all of them at the same time, what you can do is you can simply say array get of R, right? And that will return the list of answers. So in this case, we have 4 remote functions, we have 4 answers, and we get the list of answers. Any questions? Any questions at this point? So feel free to interrupt me at any stage if you have a question. You can type into the chat. So we have somebody monitoring chat, and then I'll try to pay attention to the chat as well. And also feel free to unmute if you have a question and ask via audio. All right, so the first problem we're going to be solving, a loosely coupled parallel problem, is a problem that I use a lot in teaching parallel programming. So I teach parallel programming nowadays in Python, in Julia, and in Chapel. And the problem that I like to show is the so-called slow series calculation. So in this problem, it's a brute force calculation, which is fairly simple to implement, and yet it's very difficult to optimize. So what it is it's a very well-known mathematical fact that if you take the sum of harmonic series, 1 over k, where k runs from 1 to infinity, it diverges, right? It's just a mathematical fact. Well, it turns out that if you take out any terms that contain a certain digit, for example, digit 9 in decimal notation, it actually converges, right? So if you take out all terms that in k that contain digit 9 in the decimal notation, like you take out 9, 19, 29, 199, something like that, so digit 9 is present, you don't include those terms. It converges to this number, but very slowly. So if you take some other terms, if you take more digits, then it will converge to a number that is smaller because you're taking more digits out. But for this calculation, actually, I'll be taking out digit 9 from the decimal notation. So here is the code to do this in Python. And by the way, implemented in other languages. So in Chapel compile language, it takes, so if I go from 1 to 100 million, then in Chapel it takes 300 milliseconds to compute this. And in Julia, it takes 356 milliseconds to compute this. So when I implement this on Python, it takes about 6 or 7 seconds, right? So Python is slow, as everybody knows. So this is the code to do this in Python. So here I have the slow function that simply takes the upper edge of summation, so in this case 100 million, and then it initializes the sum, and then it goes through all numbers from 1 to 100 million, and then it checks by substrings if digit 9 is not present in the decimal notation of I, so we convert the integer I to a string, and then we check if 9 is present. So if it's not present, then we include 1 over I, add 1 over I to the sum. Otherwise, we don't do anything. So let me actually run this. So I'm going to define the function. I'm going to import the time function from the time module. And then I'm going to start the timer. I'm going to do the calculation, going to pause the timer, and then print the result and the total time in seconds. And this will take about 6 or 7 seconds on my laptop. So it's a serial code. It doesn't use any parallelization yet. Okay, so actually it took a little bit longer. It took maybe with Zoom, it took 8 seconds, right? So the laptop is slightly busy. And then it produced the right answer, 13.277. So now, in order to speed it up, I'm gonna compile it with Number. So Number is a just-in-time compiler for Python codes, and the way you use it is you simply take your function, and then you add a decorator, add git just-in-time compiler decorator to it. So in this case, in this implementation, I actually have two functions. And the reason why I went from one function to two functions is because I want to do the check if digit 9 is present in the decimal notation of k, and I want to do it faster. So it turns out that number, the compiler number, is actually really, really bad when it comes to substrings. When it comes to things like this, it's actually very, very inefficient. So what you want to do, you want to check for substring in a string via arithmetic operations, and that's what I'm doing here with the combine function. So I call it combine because here it checks whether a digit 9 is present. So digit 9 is right here, is present in the number, and then if it is, then return 0. Otherwise, return 1 over k. And then here I'm going through all 100 million numbers, and then I'm simply adding combine of I, and that already has that logic checking for digit 9. But now I end up having two functions, and I JIT compile both functions. So by the way, we teach a 3-week course on parallel Python, and here I'm going, I'm skipping a lot of important details, but because we have only 55 minutes for this webinar, I can't really go through all the details, but if something is not clear, again, feel free to stop me. But basically, we're JIT compiling both functions. So this function and then this function, and then we run it. So let me do this. So here I'm gonna import the necessary functions. Then I'm gonna JIT compile the combine function, right? So compile the combine function and then compile. Well, actually here I'm defining the functions, not yet compiling them. Will be compiled during the first function call. And then here I'm starting the timer, doing the calculations for 100 million, and then stopping the timer, and then printing the result and the total. And as you can see, it actually ran a lot faster. So it ran roughly 10 times, 8, 9, 10 times faster than the previous call. So actually, in fact, let me run it again. Oops. Let me paste this again and see what kind of timing I get. Actually, yeah, the second time. So the first time I actually had to compile the code. And then as you can see, the second time, third time, and so on, I call it actually, it's significantly, it's about 20 times faster than the previous, than the non-number implementation, right? So you can see that number, just-in-time compiler in Python is really great because it can speed up your general code quite a lot. Now, what we're going to do next is we're going to combine number compilation and ray tasks. So we're going to be running using ray framework to run remote functions, but these functions are going to be compiled with number. And the way you do this is a little bit tricky. You just have to do it in 2 steps. So notice that both ray functions and the number compilation, they involve a decorator before the function. But it turns out you cannot. In these two libraries, you cannot use two decorators in front of the same function. So you have to do it in 2 steps. Basically, what you do is here's an example. Let's say I want to run my square function as a remote function, but I want to compile it with number as well. So here, first of all, you define a run compile function. That just a usual ray remote function, and then I call this ray remote function. But inside of it, it calls another function which happens to be a number compile function. It takes the number x and returns the square of that number, right? And then here I run it on 4 processes. Well, if I do this, actually, let me just paste the code. Oh, I already initialize. Yeah, I don't have to reinitialize it again. So here I define the 2 functions. And then when I call it, it runs. And then in a second, I'm going to time the slow series function, and we'll see that it actually scales quite nicely. So here's the output. I use 5, and then it returns the square of 5 via running a remote number compiled function. Now, let me skip this and then go to this code. So that's the code that implements my logic for using, computing the slow series using remote ray processes and number compilation. So I'm going to store this code in the file slow series number ray core.py, and then I'm going to run it first locally, and then I'm going to run it remotely on the cluster. So first on one node, and then on multiple nodes on the cluster. So here I define my ray cluster, and then I initialize set n to 100 million, and then here I define the combine function, which is a number compiled function. Then I have another number compile function to compute the total slow series, And then I have the helper ray remote function that will launch the slow function, number compile slow function on one of the workers. And then here I define intervals. So I break my problem. In this case, in the code, you say the number of CPU cores is hard-coded. So I'll be running this on 4 CPU cores. Actually, in fact, let me save this. So I'm going to start right now working on, in a couple of minutes, I'm going to switch to the cluster, but right now I'll run this on my laptop. So I'm going to say, let's say Emacs, open Emacs inside this window. I'm going to save this code into this file. I'm going to take this code and we'll paste it into this file inside Emacs. Here we go. Okay. And then let me exit Emacs. So here's my code. And then inside this code, what I'm doing here, actually, first thing, I'm going to run it interactively. Yeah, that will be good for debugging. So I'm going to run it interactively. So let me actually paste all this stuff, all these definitions here. And then I define the first function, the second function, and then and the third function as well. So here I had hard code the number of cores I'm going to be running on. So size is the sum goes from 1 to 100 million. So 25 million is the number of terms I'm gonna compute 25 million on each CPU core, and then I'll be passing these intervals, which is basically the interval that I'm going to be computing on each core. So that's intervals is a list of tuples, right? And each tuple just gives me the starting and ending indices to be computed computed on a given CPU core. So you can run this step. I'm actually not 100% sure whether it's necessary to export workers to the remote compile functions, but it doesn't hurt to run it, right? It doesn't take any time. And then here, we actually start the timer, we end the timer, and then in between, we do the calculations by ray remote tasks. So in this case, it's going to end course is equal to 4, so it's going to initialize, it's going to run 4 pieces, each piece remotely on a separate CPU core, and then it'll give me the timing, right? So when I paste all of this, you see that my time is actually, it went down to 129 milliseconds, which is much, much faster than the original 8 seconds I was getting for the serial non-number compiled code. Right now, I can actually run this on more than 4 cores. So let me go back to Emacs, and change the number of cores to 8, and cores, change it to 8, and then let me run this. So Python, and then the name of the function. So it is running, it's spending a lot of time on importing and initializing the array cluster, but once it's done, it's actually even faster than before. So previously I was getting 129 milliseconds, and now I'm down to roughly 100 milliseconds. So as you can see, number and array tasks can speed up your code quite a lot. So you use number compilation to actually produce a fast machine code for the function, and then you use ray tasks to distribute your workload to multiple CPU cores. So let's try to do this on a cluster. So I'll be using a training cluster, not a production cluster, but a virtual training cluster that I'm running on Arbutus at the University of Victoria. And I'm going to secure copy my code to this cluster, and then I'm going to log in into the cluster. Let me create a directory for today's webinar, and then I'm going to move the code into this directory, cd into this directory. So here's my code inside this directory. So the same code I was editing before. And what I'm going to do is I will actually modify, first I will run it on a single CPU core. I'm going to change the number of cores to 1. All right. And then also, I need to, because now I'm on a cluster, I need to load all the modules that I was talking before, and then I'm going to load my Python virtual environment that I mentioned before. And then I'm going to run a single core, so a serial job. And then inside this job, I'll run my code, right? So now I'm on node 1, and I'm running inside the serial job 1 CPU. And then to run this code, all I need to do is simply say Python, and then followed by the name of the code. So again, it initially spends a few seconds to initialize, import all the modules, and initialize the Ray cluster. And while it's doing this, here we have documentation on running Ray on HPC clusters. And there are two sections here. One is running Ray on a single node, and the other one running on multiple nodes. So on a single node, I actually suggest to to start a Ray cluster from the command line using the Ray start commands, and then connect to it from Python. So I find that's actually not really necessary. So this step is really not necessary. You can actually do it directly. You can initialize the Ray cluster not from the command line, but from Python itself, and it will do the proper thing. So it will utilize only the CPU cores that were allocated to your job by Slurm. Right? So here it ran on a single core, and then it took roughly 1 second. So let me let me quit this and let me go back to the login node. Very important to go back to the login node. Now I'm going to change the number of cores to 2. And then I'm going to exit that. And then I'm going to submit a job running on 2 CPU cores. And again, I'm just using the running a salo command from doing this interactively. So I'm going to be using 2 CPU cores interactively. Now I will be on node 1. Now I have access to 2 CPU cores inside my interactive job, and then I'm going to run the code, and it should run twice as fast. So previously it was taking 1.1 seconds. So now I'm using 2 CPU cores, and it should take roughly half a second, or 0.6 seconds, right? So it ran twice as fast. Now, if I try to run it on 8 CPU cores, it will speed up. So on this training cluster, we have up to 8 CPU cores, right? So if I submit a job asking for 8 CPU cores, you see that it will actually give me roughly 1/8 of the speed of the original serial code. So everything is great. So in this case, I'm making sure that all my CPU cores, this is very important, all my CPU cores are on the same node, right? So I'm asking for 8 tasks per node, and then for a single node, right? So this way, I'm ensuring that I'm using all 8 CPU cores on the same node, right? And that's the runtime I get, roughly 1/8 of the original runtime of 1.1 second or 1 second, right? So now let me try to run this on multiple cluster nodes. So I'm going to go into the code, going to go back to the login node, back to the code, and I'm going to change the number of CPU cores to 8. And then here is what I'm going to do is I will submit the following job asking for 2 nodes, and then 4 MPI tasks per node, right? So total number of cores is going to be 8, right? And that's what I have inside the Python code. So I'm going to run this job back on the login node. Back on the login node, I'm going to ask for 2 nodes and then 4 MPI tasks per node. Okay, great. So now I'm inside this job where I have two nodes, node 1 and node 2, and then 8 CPU cores. And then I'm going to run the code. So the code has been coded with n cores set to 8, right? So it should run 8 times faster. But spoiler, I will not get an 8 times speed up. My speed up is actually going to be a factor of 4. So as you can see, it's 1.1, 1.2 seconds divided by 4. So I got a speed up by a factor of 4, even though I have access to 8 CPU cores. So what is the problem? Well, the problem is that we actually run 8 workers on 4 CPU cores. So in this setup, we have 2 nodes and then 4 CPU cores on each node. But Ray actually doesn't know. When you run Ray this way, you simply start a Ray cluster from inside Python, right? So here's what we did. Let me go back to the login node. And then here's what we did. So we had the Ray init function right here. And we simply started the Ray cluster. And even when we specify the number of cores inside the Ray cluster, Ray in this configuration, when running on multiple nodes, it doesn't know anything about the other nodes. So it still thinks that we have a Ray, a node where it sees 4 CPU cores, and then it runs 8 workers because we ask it to run 8 workers on those 4 CPU cores, right? So the problem is Ray doesn't know anything about the second node. And here you actually have to start things by hand. So what you need to do is, let me go back to the login node, and then I'm gonna start a slightly different configuration. So here I'm gonna start the following job. So on the login node, I'm submitting a job where I'm asking for two nodes, and then one MPI task per node, right? So there'll be two MPI tasks in total. And then inside each MPI task, I'm gonna be asking for 4 CPU cores. So this is the setup that Ray can work with easily. So Ray itself doesn't really understand single core MPI tasks. It understands MPI tasks, but then it checks how many CPU cores you see inside MPI task and uses that for parallelization. So in this case, what we're going to do is, again, we're going to be asking for 8 CPU cores, but these 8 CPU cores will be available to us via on two nodes, each one MPI task on each node, and then four CPU cores inside each MPI task, right? And then what I'm going to do is next, so here I'm on node 1. I'm running this job on 2 nodes, 8 cores. And then I'm going to set these 2 variables. So the first variable, head node, stores the number of the IP of the main node in our job. So this is where I'll be starting the Ray cluster. I'm going to starting the Ray cluster on this node 1 in our job. So I have node 1 and node 2 available to me. And then I'm going to start the Ray cluster on this Ray port right here, so that later on when I start by hand, any workers, these workers I'll ask them to connect to this head node running on this cluster node and waiting for connections on this port. So let's do this. So I'm going to run this line. This is I'm starting the head node, and then here in the script it says sleep 10 seconds, so it will take a few seconds to initialize. So here now it started, and it's actually waiting for incoming connections. And then next, what I'm going to do is I have a script. So I'm going to save the script. So let me start Emacs, and I'm going to save a script into a file, launch workers. So from this script, I'm going to be launching workers. I'm going to paste these into the script, and then I'm going to run the following. So here I'm going to be starting workers. And srun will make sure that a single copy of the script is run on each MPI task. So essentially what in this configuration, what will happen is on each node, I have one MPI task, and then I'll run this launch workers.sh script on each MPI task. And so notice what here, there's the if statement. So it says that if my process ID is not 0, which means that if I'm not on the head node, then I'm going to start every worker, and then I'm going to connect to the head node of the Ray cluster running on this head node and waiting for me on this port. So let's do this. I'm going to say run launch workers. All right. Oops, permission denied. Oh, of course, I need to make it executable. Forgot about that. So here I'm starting the workers. And here we have some output, and eventually it will say connected. Ray runtime started, and I think we are good. So let me actually test this. So I'm going to go into Python, and then inside Python, I'm going to import a couple of modules, and then I'm going to connect to the Ray cluster. So let's see. Yep, we're connected to the Ray cluster, and now we can actually probe this Ray cluster. So we are supposed to have 2 nodes. Right, so I'm running the function Ray nodes, but this function is quite verbose. It outputs a lot of information. So it outputs a list, but if you inquire about the length of this list, you see that there have actually 2 nodes. So that's great. That's exactly what we are supposed to have. And then on each node, we should have 4 CPU cores. So let me run this Python loop. And so here it reports the IDs of the nodes. And then on each node, I have 4 CPU cores, right? Which is great. So now, in order to run our workflow, I will have to prepare the following submit.sh script. So here again, I'm starting everything here. So starting the Ray head node, and then starting the workers, and then I'm submitting my my workload. Right, my workload is the slow series calculation in Python. So let me do this. I'm going to start a script submit. Let me go back to the login node. Going to start the script submit.sh and submit.sh. Right. And then into this, I'm going to paste my script. So again, in the script, what I'm doing, it's a slow job submission script. So I'm asking for 2 nodes, y MPI task per node, and then 4 CPU cores per each MPI task. That means I have 8 CPU cores on each node. And then I'm starting the Ray cluster. Here, I'm starting the workers connecting to that Ray cluster head node. And then I'm doing, once everything's set up, I'm running the calculations. So let's do this. So I'm going to store this. And also, I'm going to store, let me check that I have the right number of CPU cores in slow series number in the Python code. So I should have, yes, 8 CPU cores. So everything is great. And then one other thing that I have to do, so now instead of initializing the Ray cluster like this, I need to connect to an existing Ray cluster, right? Because we started the Ray cluster from Bash, from the Linux command line. So I need to connect to it on our given head node and on our Ray port. So done, okay? And now let me exit this, and then I'm gonna say as batch submit.sh. And it is running. So let's check for output. Okay, so starting the Ray head node, great. Let's waiting for more output. Okay, so processes, okay, starting, yeah, so a lot of verbose information, but here everything ran beautifully. So we ran on 8 CPU cores, and this is the right answer. And then this is the runtime. So now the runtime here on the cluster is going to be different because the CPU cores are different than the CPU cores on my laptop, right? So don't, you know, this number is slightly higher because than what I was getting with 8 CPU cores on my laptop, because the individual cores on this cluster about, factor of 2 or 3 slower than the individual cores on my laptop. But it worked, right? It worked, but the setup is slightly more complicated, that we have to start the Ray cluster from Linux, from Bash, and then we have to connect workers from Bash as well, and then connect to an existing cluster from Python, and then do the work. So I'm going to skip this section because it's an alternative implementation of Ray data, and we have unfortunately only 20 minutes left to consider the second problem. So are there any quick questions that I can answer before I jump into the second part of this presentation? All right, well, let's continue. So for the second part of this presentation, I'm going to be solving a tightly coupled parallel problem. So I'll be solving a heat, well, actually not a heat diffusion problem, it's a Poisson equation. So it's a one-dimensional Poisson equation where u is a function of x, right? So on the right-hand side, we have some predefined function rho, and we're going to be doing this on a unit interval from 0 to 1. So we're going to set rho to the right-hand side to 2, and then we're going to set the boundary conditions. The solution at the left edge and at the right edge at 0 at 1 respectively is going to be equal to 0. So with these boundary conditions, the exact solution is going to be u of x is equal to x squared minus x. And so initially, when I was preparing this webinar, I was actually planning to do a Schwarz linear solver. So what it is you're doing a linear solver, but you're doing this on 2 processes, and then you have 2 solutions, and then you have to match the boundary condition or the interface between these solutions in the middle of the interval. And it turns out that if you do that, you converge very slowly. But there are various techniques you can speed it up. So you can use a staggered solution by basically, not doing, so at every odd time step, you're solving the equations, and then, you're solving the equations and updating the boundary conditions separately on 2 different processes. So that's a staggered solution. And then you can pre-compute the course solution in serial, and use that as the initial guess for the final solution. So it turns out that if you use all these techniques to speed up a calculation, you converge usually in 3 steps, which is not really interesting for us because it's a great numerical solution, but it's so fast that it doesn't really make sense to parallelize it. And my goal here is to do some brute force computing of a tightly coupled problem where we're doing a lot of calculations and we're doing a lot of communication, right? And with highly optimized linear parallel solver, we don't have a lot of calculations because everything just converges in 3 steps. So what I'm going to do is instead, and that was not my original plan, I'm just going to do this via brute force iteration. So here, if we discretize our partial differential equation, ui minus 1 minus 2i plus ui plus 1, right? So the index is the index of the grid point. divided by the grid step squared divided by h squared is equal to rho of I, right? So you have that equation, discrete equation at each grid point I, and then you can actually use this, rewrite this to write the solution at the next iteration. So u at point I at iteration n+1 is going to be computed using the solution at points I minus 1 and I plus 1 at the previous iteration. And then here you have bi, which is simply rho of I times h squared. So, and then you start from some initial guess. Let's say everything is 0, and then the solution, as you start iterating, the solution hopefully will converge. So here's my implementation. So here's a prototype soon to be parallel code. So it's actually a serial code, but I split it into 2 parts just to show you how I'm going to do this in parallel. So let me go back to my notebook. And let me start Python here. So the way I'm solving this problem is I'm dividing this into, first of all, I'm taking a very large number of points. So I'm going to be using 20 million points in 1D. And the reason why I have so many points is because I wanted to make sure that there is enough compute before I do communication between these 2 intervals, right? So I divided the solution into 2 intervals. So everything in blue is computed on 1 processor. Everything in red is computed on another processor. And then I'm using this equation, u of I n+1, to do the updates. And I run this equation at each internal point, right? So at each closed circle, at each filled circle, I do this update. I don't do this update at the outer, so open circles at the outer edges, simply because there the solution stays 0 throughout, right? And then at the inner point, so when we do an update at the inner point, at the interface boundary, you see that in order to compute I n+1, I need to know the neighboring values of u at point I minus 1 and I plus 1. So that means that I actually need to go and fetch the value from the other processor, right? And I use so-called ghost values for that. So here's my iteration. So here I initialize 2 solutions starting from 0. And then I have the ghost values. So ghost left and ghost right. And the way I implemented this is, so here's my usual update for the internal points on for all blue points, right? So for all blue points, u at a given point is simply equal to the summation of u at I minus 1, and then ui plus 1 minus b at point I, and divided by 2. So so this exact formula, right? And then at the interface, you actually have to use the value. So this ghost right is the value from the neighboring processor. So it's this value that I need to ship at each iteration to processor 1. So ghost right is copied from, so it's the very first point, the very first solution point in the red interval on the right, right? And it's copied to the left processor. So here it's still serial code, right? This code is still serial, so there is nothing parallel about it, but it's just a prototype code to show you the logic. So here I need these ghost left and ghost right values that I'm going to be copying at each step. So when I have this problem and I solve this problem in the file Poisson-serial.py, so still a serial code, and then I run it, I don't have a lot of time, so I think I will probably just switch to my notes. That when I run it on my computer, I get a solution. So it converges, and the way I control convergence is I'm simply looking at a solution at this field blue point, so which is the ghost, well, this point right here, right? And then I'm checking that in the successive 2 successive iterations, the difference between the solution and this point drops, relative difference drops below 10 to the minus 4. So that is the solution in the previous iteration, where it is, the solution in the previous iteration minus the solution in the current iteration divided by the solution in the current iteration. The absolute value of that number should drop below 10 to the minus 4. So I do these iterations, right? And I run it, and I print the solution, and then right here, and then I print the timing as well. So it turns out that in order to reach the relative tolerance of 10 to the minus 4, I need to do 9,961 iterations. And then my relative tolerance, my relative error drops below 10 to the minus 4. And here's my solution. So great, this is the serial code. So here I have the exact solution should be x squared minus x. So if you check these numbers, they're actually very, very far from the exact solution. And the reason for this is because at such high resolution grid, you actually need tens of millions of iterations in order to converge, right? So here in 9,000 iterations, we're not even able to propagate our solution across, even one partition of the grid, because we have 10 million data points on each grid points on each on each interval. Right, but that's not important. We're actually not really converging here yet. What we want to do is want to run until our relative error drops below 10 to the minus 4. And then we are going to parallelize it, and then we're going to time it. So if you look at the timing in seconds, it takes almost 5 minutes to run this in serial on my laptop, which is fine. So almost 5 minutes, 279 seconds. Now, in order to implement this with Ray, there is one important thing that is still missing from our code. That is, so now we are subdividing into 2 intervals, and then each interval is going to live on its own Ray worker. The problem with Ray remote functions is they are what is called stateless. So stateless means that they can run when you define a Ray remote function and then you call it, it can run on any processor that happens to be more idle at the time, right? So by default, if no computation is happening, you'll just run on the first processor, then the next Ray function is going to run on the second processor and so on, right? So we'll just pick up a more idle processor. But that's not good for us because here we have the solution U1 on one we want to have the solution U1 on one processor and then the solution U2 on the other processor. And we want these solutions to be stored permanently in the sense that we're going to be iterating, and this iteration we're going to call a remote Ray function to update the solution, but we don't want to copy the solution arrays back and forth at each iteration, right? That's going to be very slow. And that's what you have to do, copying them back and forth if you use the classical Ray functions. So the solution for this is to use Ray actors. We want to have persistent, permanent storage in between the Ray function calls. And you do this via Ray actors. So there's documentation of this, actually really good documentation. Oh, not found because, oh, I see. I need to close this, remove this closing bracket. So here's documentation. But essentially what you do is you define a Ray actor, which is an instance of a class, and it's going to be persistent between different Ray function calls. So here we have a class, right? But this is a Ray remote class. So it's a class with a couple of, actually with one variable, so self-array variable, and then a couple of methods or functions, right? And then when you initiate this class by simply calling the class name and then remote, so same for function, right? For function, you will see in Ray function name and then dot remote. So here we have the class name and then dot remote. What this will do, it will create an instance of this class on one of the workers. But it turns out that in Ray, a class is permanent in the sense that we're not calling any functions yet. We just initialized the actor, this instance of the class, and it's going to sit on that worker. So this is a way to initialize permanent arrays on Ray workers. So let me show how this works. So here interactively, I'm going to import the modules. I'm going to initialize a basic Ray cluster. And then here I define this class. So this class has an array, right? So here's an array, which is called safe array. So this is a persistent array variable. It's going to be stored in between the function calls on the same worker. And then I have a couple of methods. So a method to store the array, and then the method to get the array, right? So here I initialize the class. So if I see storage actor, well, it will just tell me it's an array storage instance of an array storage class. An actor means instance of this class. And then I'm going to store an array. So here I initialize a NumPy array locally on the control process, and then I'm going to send it to a worker. So I'm going to call a function store array. And what store array does is simply writes this array that I pass as a function argument. So the function is store array. I pass it to the instance, and then it's going to store there inside the self array variable, right? So here we go. Now it is stored there. So it's actually stored permanently on the worker. And then to get it, I get to actually get it back on the control process. I simply run the get array function. So here, get array function. I run it, and then I can actually print R. And here's here's array copied back to the control process. So now, if you have multiple workers, what you want to do is, let's say you have 2 workers, but you want to do it in a scalable fashion. Again, you do these lists, right? So I cycle through, let's say, 2 workers. And then, so here, first of all, I create 2 workers. So here now I have 2 workers with some array storage on each, right? So there are 2 workers. And then in order to store an array, I'm going to say store array remote, and then on the first one, I'm going to store an array of 1s, and on the second one, I'm going to store an array of 2s, right? So that's what's done here via this yellow highlighted code. So here we go. And then in order to get the results, I simply do this. right? So I call array get on one of the workers, so either worker 0 or worker 1, because workers is now a Python list. And then if I want to get both results at the same time, I can do something like this, right? I can do this, and then I say array get of R, and that will print back the result with both arrays. But the important thing is that the arrays are stored there permanently in between the function calls as well. So, and now what you can do on these workers inside this class, well, you can do everything. You can, we're going to be using NumPy. So here's an example of solving, we're not going to do this, but it's just an example of solving a linear algebra problem, right? So here I have a class where inside this class, I have a function local solve, which simply takes a local array A and then takes a local array B, and both of them are stored permanently on that worker. And it simply solves the linear problem AXB, right? So that's the NumPy linear algebra routine, and then it when I do the whole pipeline, so here I initialize the worker, I store the right-hand side B on the worker. Then notice that the left-hand side actually not stored separately. It's actually calculated during the initialization call, right? So when I initialize the worker, when I initialize the actor, or when I initialize the actor on the worker, I store the left-hand side array right here in the initialization call. And then the next function call is local solve that solves the equation, and then I get the solution by calling the getU function that copies the solution back to the controlled process. So now, how do I do this for the back to the Poisson solver? So the Poisson solver, essentially the code is very similar conceptually to the previous serial code, except that now I use array worker. So I still have the left and right side. I have just two intervals. But on these two intervals, so I initialize two workers. And these two workers are, they have the actor, which the instance of the class array storage, which now has this function local solve, which now does my solution for the Poisson equation. So the same serial solution you saw before, but now I do this for all internal points. But then I have to have the if statement here. So if I'm working on the left interval, so if side is 1, then I need to take the ghost value from the right. And then if I'm working on the right interval, I need to take the ghost value from the left, right? And those ghost values themselves, you have to call them via array remote functions, right? So the ghost on the left and the ghost on the right. Well, these have to also, because the solution is permanently stored on the workers. So actually I have to call the get last function and get last value and then get first value function. So these two functions will take the the edges near the internal boundary and then copy it back to the control process. And then what I do here is I simply follow exactly the same logic. So I do the local solution with these ghost values, and then I calculate the difference. And then if the difference is smaller, while the difference is still smaller than the relative tolerance, that I start iterating, otherwise I stop. And then every 100 iterations, I print the solution, right? So I don't do this more often for two reasons. First of all, there will be a lot of printout, and then also whenever you get the full solution, right? So you get the entire solution, that's quite a lot of communication, right? And then I time my code. So here I start the here I start the timer, here I end the timer, and then print the solution, print the timing, and so on. So now when I run this on two CPU cores, you see that instead of 5 minutes, I get like 40% improvement. So not quite twice as fast, but almost twice as fast. So the reason why it's not 100% parallel efficiency is because now I have a lot of communication, right? So I actually have communication between the workers and the two workers and the control process. So for a scalable version for any number of workers, what you need to do is you have exactly the same class, well, very similar class, but now you have slightly more complex logic. So now you have any number of intervals, right? And you have to make sure that the intervals treat the intervals compute the use the right ghost values, and you're communicating these ghost values. There is some logic about the ghost values here, and then here actually computing the ghost values, right? And everything, by the way, is done by NumPy calculation. So notice that nowhere on the workers I have explicit for loops, right? So I'm doing everything by NumPy, which is important to make sure the code runs fast. And so the code runs, and then when I run it on 4 workers, then I get further speed up. So one very important performance tip, very important, is that whenever you launch multiple calculations of multiple workers, you cannot do something like this, because here I'm cycling through all workers, through all CPU cores, and then I'm calling this local solve function to solve the local problem. So when I do this like this, every call to array get is actually a blocking call, which means that you go to the first worker, right? So you have the first loop iteration, then you start your calculation, and then here you're waiting for a calculation to finish before you go to the next one, right? So in fact, this will do the calculation, but it will do it serially, which is not what we want to do. We want to run calculations simultaneously on multiple CPU cores. So to do this, we cycle through all workers, but we do it without calling array get, right? So here we initialize the calculations, and so starting a array remote function is not a blocking call, right? So it starts the first function, then starts the second function, starts the third function, and it doesn't block on the control process. And then later on, after we started all these workers, if we need to get the results, then we run array get to get the results. So now running this problem, almost done. Running this problem on one cluster node will give you the right timing. So here, unfortunately, I have only a couple of minutes left, so I cannot really show this demo live. I was hoping to do it live, but everything is in my notes. So here I'm running one cluster nodes, asking for just for a single processor and running the problem serially. So it takes 2,200 seconds. Then running this on two processes on the same node, and then running the two-processor version of the code, so Poisson dual.py. So that gives me like 35–40% speed up, right? And why we don't have a perfect 50% speed up? Well, the reason is because, as I said, we now have a lot of communication. So we have 9,900 iterations, almost 10,000 iterations, and then each iteration we actually have to ship the ghost values from each of the workers to the control process and then back to each of the workers, right? So there is a lot of communication in this problem. That's why it's called a tightly coupled parallel problem. And then when I run it on 4 cores, I will get a further speed up. But again, it's not exactly by a factor of 4 compared to the original calculation. There's still quite a lot of communication, but you see that it's quite nice speed up, especially compared to the two-core run. I get here I get almost a perfect scaling. Now, again, to run this on multiple cluster nodes, I have to launch the array head node on the on one of the nodes and then I have to connect from workers on all other nodes on the cluster. Right? So we've done this before. I won't go into the details, but when you do this, you'll see that you will run into a problem. And this problem, so this actually is something that is not mentioned in our documentation, and it's not mentioned, I didn't see it in RAY documentation. So what's happening here, if you just follow the steps that I described previously for the slow series problem, what will happen is that RAY decides to use, it doesn't bind workers to your CPU cores. So it sees that it has 8 CPU cores, and it will start, let's say, 4 CPU cores in this example, and it start 4 workers, but it will not bind those 4 workers to 4 CPU cores. It might actually happen that you might have 1 worker on one node and then 3 workers on the second node, or you can have all 4 workers running on one node and then 0 workers running on the second node. So I found out that you actually, in order to bind workers to CPU processes, when you initialize your class in the class definition, you have to specify that the class uses a single worker. So you have to issue this parameter when you to this decorator when you describe the class, and then things will happen nicely. So it will actually bind the workers, those actors, to actual physical CPU cores, right? So in this case, I have 2 nodes and then 2 CPU cores per node. You see that 2 of the workers run on one node. So those are the IDs of the array nodes. And then 2 other workers are running on 2 other nodes. And then things scale beautifully. So here's scaling on, I did scaling on CEDA yesterday. And as you can see, the problem scales quite nicely as you increase the number of CPU cores. But at some point, the scaling stops. And the reason for this is because you are simply having a problem, you're computing a problem that is way too small. So in this problem, when you take 20 million grid points in this one-dimensional Poisson solver, and you break this into intervals, if you start breaking into more intervals, you will have very little compute per each interval, right? And a lot of communication. So all those boundary values will be flying between those intervals at each iteration, right? So the solution, these can actually scale very well to much bigger number of cores. But the solution, of course, is you have to be solving a much bigger problem than just 20 million grid points. So I'm out of time, unfortunately. If there are any questions, I'm happy to stay around. I understand there's quite a lot of material here that I covered, but everything is in these notes. Everything will stay here. Feel free to send me an email. So our email address is training@west-digitalresearchinfrastructure.ca. So send me an email if there are any questions. But all examples I showed you today, they will run perfectly on any production cluster. And yeah, and I will stop here.